Professor did a very good job introducing me. But we first met in EPM in 2023. Yes, it was very, 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 very hot. Yes. But right now I'm doing a postdoc at the Kids Research Institute, doing actually none of this, more infectious diseases. But even then, it's more statistics. But I won't be talking about statistics too much today. Okay, so dynamical systems 1001. I don't know how much dynamical systems like the room knows, and there's probably going to be some really good people here as well. But just make sure everybody's on the same page. The way I like to say is dynamics is whenever you have a system and there are aspects of the system that are time varying, we can kind of write it in two different ways mathematically. The first way is we call the autonomous dynamical system, where you let it evolve on its own, and you can write it in the most general form as just a differential equation that way. The other way is just the non-autonomous version, where you have your same thing, but there's some kind of input from the outside that can be varying over time. So you have a normal term plus a driving term. And normally when we try to take this and drag it into the applied time series analysis space, we have a few kind of questions you want to ask. Traditionally, when you write down a system, the traditional way would be, well, we want to ask, what is the global behavior of the system? If we let the system run, are there stable solutions? What's the effect of perturbations? Is it structurally stable, that kind of thing? But oftentimes in the real world, you get given time series, you can't write this equation down, right? So we want to do two different tasks instead. So one thing is state estimation. We have something that we observe. Can we infer what the unobserved parts of the system are? That's number one. Or can we predict what it's going to be like in the future? Now, if we want to predict stuff, that means we need to know something about F, but we'll get to that next later. But essentially, this is kind of the framework that we're going to try and approach the time series analysis aspect. Instead of just kind of assuming it's like a Gaussian process or something of the sort, we're going to try and grab ideas from dynamical systems and use it for time series analysis. So the typical time series analysis problem is you have some kind of system with a true hidden state, and the hidden state, maybe it's oscillating or something of the sort. And let's say it follows a dynamical system in that sense. But we don't know X, we don't know F. We cannot know X, we cannot know F. It's impossible for us to know that. What we can do is we can observe this. So we have this black box, we can observe it. And oftentimes we will represent this observation as a function H, where we lose information, we lose detail along the way. So let's say if this is a three-dimensional system, we observe it, we may only observe one component of it. Right? We lose information about Y, about maybe if this is X component, we lose information about the Y and the Z. And the question is, the time series analysis problem is, given we have this time series, how do we maybe figure out the behavior of this black box, if possible? That's one part, the system characterization part. The other part is, how can we predict what happens in the future? That's the more interesting in the application side, right? Because oftentimes we do math because we want to model and try to predict things. So I like to think about it as two sides of the same coin. One part tries to focus on more understanding. We don't really worry as much about prediction. The other side is more focused on accuracy of prediction, because you can have a method that predicts very well for the next two-step time steps, but it generalizes very badly if you try to predict multiple steps in the future, because the model you make doesn't actually capture what's in here. It's just good at that, that small time step. But the other way, if you want to try to learn about more understanding, you may be able to make a model that predicts very badly in a short time scale, but in the long run, it behaves roughly what you expect. It's in the general behavior. So these are the two different aspects we want to balance. And the ways we do time series analysis, I'm going to kind of split them in a very artificial way, trying to kind of split them into two categories. But they are two sides of the same coin, right? So whenever you have things in time series, we have things like periodicities, we have chaotic behavior. So things, trajectory splitting of very sensitive dependence initial conditions. But when we want to move into the dynamical system space, right, we want to go from periodicities here and understanding how does it look like in this kind of black box dynamical systems with the multidimensional state here. Well, the ways they are linked together, because they're two sides of the same coin, periodicities in what you observe can actually be linked to periodic orbits in a dynamical system, right? Fractal structures can be linked to chaotic behavior when you're trying to do time series and it's very hard to predict. That's not necessarily all the time, but there are links to that. But the more interesting distinction is in the typical methods you would use to tackle the problems, right? If you kind of work mostly in the time series, if you just work directly on a time series, oftentimes you might be looking at things like moving statistics. So you're moving averages, all that kind of stuff. You might be looking at autoregressive processes and trying to fit regressive processes. You maybe look at first return maps or hidden Markov models, right? So that one's more Bayesian type thing. And if you want to work in state space, so looking at the black box, if you can try and retrieve the black box, then, actually I just realized. This should be on the left side. Sorry, frequency spectral analysis is on time series, yeah. But if you want to move to the right side, you might be looking at things like nearest neighbors, right? Because now you have positions in space, you can look at your nearest neighbors. Whereas if you do just the scalar time series, you can't do that. Or recurrence plots, persistent homology, because you have a point cloud, you can now work with actual spatial things. Now, ordinal methods is kind of like in between because it dips into both areas. That's why there's a little asterisk there. But the idea here is that you can't use state space methods for everything, and some things might be better to use time series analysis methods. It's just you balance based on the task that you have. So that's just the context. So now I'm going to go through a bit of embedding theory because that will help us bridge the two methods together. So the main aim is to basically form, embedding theory's aim is to try and form a bridge between using time series methods and state space methods. The idea is if you have a problem that's presented as a time series, how can we transform the problem into like a more state space dynamical systems framework, do your analysis on there, and then transform back. And the thing that links these is essentially embedding theory, and that's why we embed things. But I've gone on talking about embedding. I haven't said what an embedding is. So this is a slightly more formal definition. And there's a lot of words there. And I just put that there mostly because don't care about that. Just look at this picture. Essentially, remember that black box we saw before. This is like a black box. So I've used the Lorentz system. People have seen a Lorentz system before, yeah. So we know there's chaotic behavior, there's the two lobes, there's the saddle point, all the nice fractal structure there. But essentially, we have a black box. Suppose the black box is the Lorentz system, and it follows some kind of evolution along the attractor given by f of t. T here, I think, yeah. So small f means this is the true dynamics. Now, if you observe the Lorentz system, maybe you'll get some kind of time series out, which is this thing at the bottom. And your question perhaps is, can I try and predict, or can I try and learn about this information purely from this time series? Now, there are ways to, for now, I'm going to say that this psi here, let's just call it the embedding operation. But it's a way for me to transform this into here, right? And the rule is, if I can define a way to go from here to here, such that, number one, they look the same, topologically they look the same, but more importantly, the dynamics are preserved, right? So something moving along here is similar to a similar motion here in a very simplified way. Then we say that whatever operation we set here is considered a valid way to embed. So an embedding is literally just, how do I go from here to here? If this is a valid embedding, I can basically say that these two things are equivalent, right? And notice if I go from here to here, I don't actually need information about this true state, which means I have a time series. If I can embed it, I can do all my state space methods in this space. And because I know this and this are equivalent, whatever I do here will be valid on the true system that I can observe. So in a way, we're kind of trying to skirt around the fact that there are some aspects we can't observe directly. Yeah. Does that kind of make sense? Yeah. So in practice, what do we do? So I said there is this thing here, and I kind of alluded to. Oh no, yeah, I said there's this side here, but I didn't say how you're going to do it. And there's a hint there. There's a in the axis and kind of hinted a little bit. So and this is where I spent a bit of time on a very. So this is a very old problem. How do we construct the embedding? Historically, we had these things called integral differential embeddings, which were, if you have x, you take the numerical derivative as one component, you have x, and then you take the smooth integral, right? And what will happen is, if you kind of struct this into one vector, so you convert from what was scalar time series into, now I guess here, three-dimensional vector, and you plotted it, it would be an embedding of sorts. I can't remember if there's proof whether this works, but this was tried. And it's nice until you have noise, right? First thing is, if you have any amount of noise, all these numerical derivatives are going to start breaking down very, very quickly because your noise gets amplified. And even if you don't have noise, there's only so much smoothing you can do before your dynamics just get washed out and the upper dimensions are not useful anymore. So in terms of, yeah, you can go from scalar one dimension to 3 dimensions, and that's about it, right? You can't go much further than that. More recently, so this is very old. More recently, if you guys have heard of reservoir computers, well, recurrent neural networks, machine learning. So a lot of these ideas here also do embed in a more indirect way. So the idea is built into that. So things like your machine learning, your time series prediction machine learning, actually underneath the hood, there's a lot of work being done to link that to dynamical systems. Because underneath it's actually just a dynamical system. But you have the very new stuff, you got the very old stuff, and then in between is the stuff that everybody uses now because it's very easy to do and generally kind of works. It's called delay embedding. And remember, the aim of the game was to go from linear, one-dimensional time series, scalar time series, into more higher dimensions with state space and kind of thing. And there are 2 ways of that people do it. The most common way, which basically dominated the methods for the last like 35 years, is you take the time series here, and then the other components, you take lagged versions of it, right? And you extend it into this, from 1 dimension, you make it into m+1 dimensions, right? Now, this one works. This method is very easy. You can code it up. It takes you 30 seconds to write it up in Python. Why is it hard? It's because it's very hard to figure out how many lags do you take, right? You have this scalar time series. You take xt-1, t-10. Which one do you do? Also, how many dimensions do you go up to? That's also another question. But if you can answer those questions, kind of works. The problem is, and I'll give an example later, what happens when you have data where you have multiple timescales? So you have a really fast oscillation and a very slow oscillation at the same place, but maybe the fast oscillation is very small in magnitude and the slow oscillation is very large in magnitude, right? The problem with Parkin's embedding in this default form is that you really only include one time scale, right? Inside, you choose one lag. You cannot possibly make the dimension really large, but then what happens when you have limited data, very large dimension, your data becomes very, very sparse, right? So all your things like wanting to do your machine learning or all your calculations in that space now become quite ill-conditioned because you just don't have enough points, right? 1-dimensional space is small, 2-dimensional space is all right. 3 is nice enough to have chaos. 4, 5, 6, 7, you start having data problems, numerically speaking. Now, this is basically still the main one that's being used, but since I should know this because this was my thesis. Since I think the year 1999 to 2000, there was increasing small pockets of people thinking, well, how are we going to extend these delay embedding methods to cases where you have data with multiple timescales and multiple magnitude scales? So the most general way would be to say, well, every lag can be different. So you can say xt minus 1, and then suddenly go xt minus 7, and then maybe xt minus 502, right? So you have a very big time scale and a very small time scale. But that is combinatorially difficult because here you only have to figure out two things, the tau and the m. Here you have to figure out m things, right? And you don't want to manually check every number because you choose a combination, then you need to evaluate whether it's good. That's going to be very tedious, right? So this one is a bit special. And what happened was someone proposed something in 2000. Then for 10 years, it just got buried. And then it popped up again in 2010. And then it disappeared again for another 10 years. And then someone else did some work in 2021 or 2019. And now it's gaining a bit more traction, but I have a few comments on that later. But I mentioned these words, tokens embedding here, and delay embedding. So the way to just think about it is, I said that this method of making that vector produces a valid embedding. The person that proved that was Flores Tokens, and that's why it's called a tokens embedding theorem. Now, the main thing to take away from this is the assumptions that it makes. I've tried many times to read the proof, and I've given up halfway through every single time. It's quite complicated, or at least for me, it's very complicated. But the assumptions are easy to understand, at least from a time series analysis perspective. So very computational stuff. So the main thing is it assumes that you have no noise, and it assumes that infinite precision. So that your observations are infinitely precise and there's no noise in your data at all. And if that's the case, actually, you don't even need to worry about what lag to pick. You can just pick any lag, just pick one, and you just need a big enough dimension and your embedding will be fine. Computationally, that's bad because you always have noise. You're stuck at best your 128-bit precision. And we don't want to work in 100-dimensional space. We want to figure out how to make it as parsimonious as possible. So embedding theorem is good, but most cases it breaks the guarantees. So the idea is what is the implications of this then? Well, hold on. It's missing the bit. Well, the message there is then not all embeddings are made equal. Because we can't fulfill this condition, right? No noise and infinite precision. The result is that when we do an embedding, when we select the tau, we select the m, some combinations will be better than others. If we had this, it doesn't matter what combination we take, it'll all be fine. But because we do not have that assumption, we need to actually optimize this tau and this m. And to illustrate what I mean is this. So this would be a time series from a sine wave, right? If you write this as ODE, it would be a second order linear ODE, or two coupled pairs of first order equations. So getting about this as two-dimensional. So ideally, if we embed this, it would be a two-dimensional 6-6, right? So what happens? So it's colored here by the phase. So dark here is maybe small angle, and then it goes back here. Now, when we take a very small tau, small lag, and let's say our observations are noisy, this is the embedding that we get. Now, if you look at so we have noisy observations and noisy data. We look in and we say, okay, that's a little square we see. There are parts in there whose state is very small angle and whose state is very large angle, roughly in the same vicinity, right? This is an example of what we say is a very bad embedding, because in delay embedded space, there is a lot of uncertainty as to what the true underlying state is, right? By just looking at one point, I could have an angle of, I don't know, like maybe this is like 130 degrees and an angle of 20 degrees, right? There's a lot of uncertainty in there. Whereas if we take a different leg, for example, let me take a bigger leg, it opens up the space a little bit, and it basically makes sure that you don't have that ambiguity in your state estimation. So essentially, when we do this process of delay embedding, which is also called, another way to call it is space-based reconstruction, we want to make sure that there is minimal uncertainty, as best as we can, on what our inference of the true underlying state is. So that's the first condition that we want to aim for. And this is also happens to be the same as we want it to be well unfolded. So oftentimes what you'll see is if your leg's too small, it'll look like everything's on a diagonal. Then it opens up. But if your leg's too big, right, if you want to say, you want to plot xt and xt minus 1005, right? Those two observations may be so irrelevant, decorrelated from each other, that what you end up is maybe this circle kind of unfolding, collapsing on itself and getting a bit tangled, which again causes the same problem of, imagine where the knots are, where the tangles are going to be. There is going to be uncertainty as well. So there is this nice Goldilocks sweet spot, ideally where there is minimal uncertainty. So that's what we mean by well unfolded. And I use these specific terms here, which was introduced in the 2000 paper that I mentioned by Kazagli, which essentially says if it's too small and it's all along the diagonal, we call that irrelevance because, we call that redundance because you include so much highly correlated data that they're all close together. If you include timescales lags that are too large, we say that's irrelevant because you're including uncorrelated, not useful things inside. So that's the first rule. But we want to also, we don't want to just take any tau. We want a tau to actually have meaning, right? Because the aim here is not to make models for the sake of making models. We want to make models that are interpretable. Because when someone asks, why did you choose that? You can explain, oh, because this tau relates to a time scale or somewhere. So we want to make sure the time scales are interpretable and related to the dynamics to observe. And oftentimes, you use the dynamics to choose the tau anyway, so that's fine. And why delay embedding is really nice is because if I want to make a bigger, higher dimension, I just add more legs after that. It's very easy to just pick a number and then let's say I want to make 10 dimensions. You just plot 10 legs, and it's very easy. And I mostly included this because this is my baby. This was what I spent 2 years looking up. Essentially, it's a timeline of where these delay embedding methods kind of sprung up. So Hawkins was 1980. He first proved that you could do this delay idea. In fact, a lot of biologists were actually using this idea. They just didn't know why it worked. Hawkins did that formal proof of why that works. And if you look at the paper, there's a very, it's typewritten. And there's like a very nice drawings on that because basically he had a very nice fluid mechanics experiment that he did. Very cool. But in 1980s is that. By this time, people had started using delay embeddings a lot. And then later, we had this really big development in 1983. Has anybody here heard of Grasberger and Focaccia? So has anybody here of correlation dimension? Fractal dimension. Fractal dimension a little bit. So it's in chaos theory, that's one of the invariants that you use to estimate how things are scaling, right? And so Grasberger-Focaccia basically gave one of the first ways we could estimate that fractal dimension from data using the GP algorithm, and it was underpinned by embedding reconstructions. And then shortly after, basically all this was all the pioneers, right? Then we had basically saying, how do we select the legs and embedding dimension? And that was Fraser and Swinney, which I believe they wanted to do it on biological data as well. And then Sauer, which was slightly after that, linked all this together and said, if you can estimate correlation dimension, I can tell you that you only need 2 times that as your maximum required dimension, and that's good enough to create an embedding. So now we have an upper limit to how big we need to make our delay vector. And 1991, so this guy is the guy who first came up with the idea of not all embeddings are equally good. There are some good choices and some bad choices. How do we tell you which embedding is good? So that's this guy. And then Panel was kind of tied it up again and said, Sauer said you need m equals 2dc, but perhaps maybe you don't need 2 times the dimension. You can actually do a bit less. We want to be more efficient. Panel basically gave the earliest algorithm to do that, which is the false nearest neighbors algorithm. I won't go into the details of how these algorithms work, but I guess it's just more like just to bring up the name so that if you guys want to search on your own, you can search. For reference, this false nearest neighbors thing is still used as the main method of figuring out how big of a dimension you go. Now, that was basically, here was all the foundation you need for delay embedding already. All the mathematical theory was kind of laid out. And from 1998, this is where all the non-uniform, the interest in non-uniform embedding started happening. So 1998, some people from UWA were interested in using information theory to figure out how to select lags in a non-uniform way. And this was coming off from Kazagli in 1991. And then there was a brief period of about 20 years. I would like to say basically there's only 1, 2, 3, 4 main methods that kind of got proposed, of which this one doesn't really work very well. And this one is meant to work, but people can't seem to get it to work. This one, nobody understands how it works. It's very confusing. And these two are essentially very similar. These two are generalization. Uzal is a slight generalization of Aura. And then Kramer built up on Uzal. And then that's that. But that's basically the history of that. And this slide is mostly just to show off, not the names, but more so the keywords, things like embedding, like mutual information, false nearest neighbors, just so that if you guys are interested in it, you have the words to kind of just search it up and bring more things, find out more about stuff. So that's the brief history. But that's not that important now. More important thing is how you're going to do it. You get given a time series. I want to know, how do I pick my tau and how do I pick my m, right? Because that's what you're going to need to do when you get given data. Someone's going to say, analyze this for me. So first question you asked, is there multiple dominant and disparate timescales? If yes, sorry, you have to use probably non-uniform delay embedding. But oftentimes you can just say no or pretend it's no and just go with uniform delay embedding. And I'll give you an example where you have to do this. But for most cases, you can just do uniform, which means we really only have to do 2 selections, right? We need to select the lag and the dimension. The lag is very easy most of the time. We just say, is there a single periodicity? So there's a general, like the thing repeats itself roughly every 5 or maybe every 20 steps, plus or minus a little bit, because maybe it's noisy or it's a biological system, it wavers a little bit. Then we just say the lag is 1/4 of that. So if it repeats roughly every 20 steps, we take the lag as 5 steps. Easy. If your data doesn't have that, right, and it's kind of just a bit messy, you have the next best thing, the next easiest thing is what we call the minimum mutual information, where you take it's basically taking it's like autocorrelation, but non-linear. So autocorrelation measures linear correlation in the time-like versions. Minimum mutual information is very similar, but it's a non-linear generalization of that. So you would do that, and there's lots of packages that do this for you. So if what language do people normally use here? MATLAB, Python. Okay, so I think there's a dynamical systems package on Python that does this. Otherwise, you could these ones mutual information you might take an hour to code up, but this one you can just look and pick the number, right? If there's people in Julia, I would highly encourage, if you want to play around with embedding stuff and you don't want to code any of it yourself, Julia has a very nice 5 packages that they can package into one package. So you install that one and you can play with all the tools, and it has the latest ones like not this, but all the latest ones here. You can even run them yourself. I know, and if people want to show you the website where it is. But if you don't want to do those two, there is also PCA embedding, so principal components analysis. It does use PCA. People know what PCA is, right? Principal components analysis. I won't go into too much detail of that, but know that that is an option. But usually these first two are good enough for most cases. So you take this and you would get a lag, but then the next question you have to ask is how many dimensions do you do, right? You do 2 dimensions, 3 dimensions, 4 dimensions. And here Sauer said you just take twice the correlation dimension. But that implies you can calculate this correlation dimension to begin with, which is actually very hard for real data. So oftentimes we use the false nearest neighbors algorithm. Another one is we take 1 dimension, train your predictor, and then see how does predict, increase the dimension 1 step, train the predictor again. Does your prediction do better? And you do that until increasing the dimension does not help anymore. Oftentimes because of numerical problems with the large dimension, data sparsity, or it just saturates, right? Alternatively, you just pick an M such that the dimension times your lag does not really exceed or is roughly about the same as the main periodicity you have. Because if it's kind of an oscillating behavior, there's no point including staff pass mode oscillation. But the nice part is, if you go in a toolbox, they will do it all for you. So before the toolbox existed, we would have to implement all of this ourselves, which would have been very time consuming. But I'm very grateful that someone has gone through and kind of implemented all of it. So I'll show you the package of how it kind of works. But end of the day, don't think too much about it. Just take a lag, take a dimension, start there, play around. And if you want to start predicting things, embed it, do the predictions, and see if it works. If it doesn't work, ask yourself, is it because of the embedding, or is it because of the predictor? Which nowadays, I think the flavor of the month is feed-forward neural networks, right? Or, yeah. So you have to ask, is it because my embedding is bad, or is it because my neural network architecture is bad? So don't worry too much. Just start and play around with it. So case in point, I'm bringing back this. I'm going to bring back this graph just to give like a case study of the typical workflow of how that's going to work. So we have some system, we observe it, we get a time series. So really, this doesn't exist in our mind. We only have the time series. We do a delay embedding, so we get that phase space now. Yeah. This is what happens when you change the lag. So here I'm using the X component. So it's as if I'm only observing the X component. Here I'm only observing the Y component. Here I'm only using the Z component. And these are increasing lags. And they're all 3D embeddings. And so what we see is for X and Y, when the lag is really small, you get the diagonal, right? Really bad embedding. But then as you kind of increase it, you get the nice unfolding. But there comes a point where your lag is just not useful. It's too big. We start heading into the irrelevance territory. And so it starts collapsing on itself. And clearly that's that's not right. That's not the attractor that we want. But so X and Y, seems good. But if we try to do it with the Z component, so this is a pathological case. If our time series was the Z component of the Lorentz system, and we try to do the same thing, we would get something. It looks kind of similar but not. And then same thing, it collapses. But what's the main difference between the two? Between these two and the Z1? So these two have the two lobes, right? Lorentz is there's three main. Lorentz has three main fixed points. There is a saddle in the center, which is the source of all the nightmare and the cool stuff. And then there's the two fixed points, which are the two lobes. And remember, if something's in a valid embedding, there needs to be a transformation between the two, which means your periodic orbits your fixed points must be preserved, which means if this is a valid embedding, it needs two lobes somewhere. But here we have the Z component. There are no two lobes. So this just illustrates that if your observations are observing the wrong thing, you can't actually make an embedding. So, I mean, oftentimes this is very rare, but this just illustrates the fact that oftentimes it's possibly due to observations. In this case, it's actually due to the symmetry of the Lorentz system. But just an illustration. And then after this, you would have in state space, and you would do your predictor. You train your one-step prediction normally in the state space here. So that's an example of if you have just generic time series data. But what happens when you have time series data that looks like this? So this is an example I mentioned before, where you have one large time scale with a large magnitude and large time scale, and then small oscillations, which are also important, but small magnitude and small time scale. And I would love to share this data. Unfortunately, I can't because the last person that owned that data, that has ownership of the data, has just passed away last year. If I remember correctly, so this data is they took a poor lobster and kind of found one of its neurons, and the lobster just moving its hand like this. And this is the I think it's the voltage potential of the neuron. Essentially, what's happening is there are moments where the neuron fires in what we call bursting mode, and then after a while it rests for a bit in this repolarized bit, and then depolarizes and then repeats, right? But a few things to note is the number of spikes in this is not the same each time. The width of this is not always the same. And if you try to do a spectral analysis of this, it would not be helpful at all. You might be able to get, maybe if you're lucky, that waveform, but getting that small bit is also hard, right? I've tried. And so you look at this and say, well, why can't we do a time delay embedding? Let's just pick one leg. Well, do we pick the big leg? We pick the big one. You're going to have the big loop, but all this is just going to look like noise, but it's definitely not noise. If you pick the small one, you're going to occasionally see this, but then all this is just going to lie on the main diagonal. It's an example. It's very rare when it occurs, but it's an example of where you would need non-uniform. So you need to take two legs, for example. So this was a method that we kind of looked at, and I think the main one you want to see is that just look at. So these are your mutual information stuff, but look at this plot here. This tells you when there's a big hump. It tells you that's one of the lags that you might want to consider. And what we see here, there is actually a hump early on, which corresponds to the fast time scale. So these are time lags. There's a hump here early on, corresponds to the fast time scale. And then there's a later hump, which is that slow depolarization, the long time scale. And when you start embedding in 2 dimensions, and this was us comparing a few methods that try to do the same thing, essentially your small time scale unfolds for the small loop. This is your bursting part. And your large time scale produces that big loop. And in 3 dimensions, you get this attractor-like thing, which looks like that, right? And the other methods do something similar, but they kind of mess up the time scales a little bit. The nice part about this is that now you have something that's well unfolded in state space. You got like 3 dimensions. You can go and put it in your neural network and kind of predict forward, and that's exactly what we did. So this is just what call it? The 10-step prediction error. So we train a neural network to predict 1 step ahead, and then we fed that 1 step backwards 10 times, so it does a 10-step prediction with only 1 initial condition, which is the starting part. Now you might think, stocks does really badly. The spread is so large, but one thing to note is the median is actually lower. But actually, the point here is actually not to say that it predicts better, because these errors are not great, right? You think, well, what's the point of doing this non-uniform delay embedding? Well, when we look closer, right, this is what the real data looks like. And when you try to train those you train the one-step prediction, and then you try to predict 10 steps ahead. When your embedding is not quite right, you actually struggle to reproduce those spikes. Because when you enter into that region where it's a fast oscillation, all the trajectories are kind of crossing. So the neural network predictor is very confused as to where's the next step going to be, right? Because it's getting contradictory information. But when you do stocks, at least, so these are the two comparison methods. When you do the non-uniform delay embedding properly, you actually get that spiking behavior being clear, at least, right? So this is an example of, we're not trying to predict for accuracy, but we're trying to learn the dynamics itself, right? Which embedding allows you to learn the inherent behavior a little bit better. So that's end of the first third. How am I going for time?
Yeah, it's okay. Like 4 yet.
Oh gosh. So is there any questions so far?
But the embedding part.
Yeah. Next part will be quick, and then I can get to ordinal stuff. But if you guys need a break or have any questions, please let me know. So here, this section is, I'm going to talk about what we call the cursor dimensionality. Phase-space reconstruction is great. You increase dimension, but it also means you have high dimensional data if you pick a large M. So poor computational scaling, because high dimensional data, you need a lot of data, and a lot of numerical algorithms work poorly in high dimension. So that's a problem with dimension. But then also you want to ask, how good is your method hold up to noise, right? And this is the question I dread the most when I submit a paper, because they ask, how does noise affect your method? And then I'm like, I have to go and spend 1 month coding up some script to test all the different noise cases. When we do dynamical systems methods, there are two main types of noises we have to consider. So the first one is dynamical noise, which means the noise is actually inside the system and affecting the dynamics, right? So that's like me bouncing a ball but shaking the table at the same time. The shaking of the table is going to affect how the ball is bouncing. I can't do anything about that, because I can only observe the system, right? Unless I know how I'm shaking the table, I can't do anything about dynamical noise. The other one, I can deal with it more, right? Observational noise is the ball's bouncing, but I'm measuring the height, but I maybe can't measure it accurately because my eyes are not very good. Or maybe the ruler is kind of a little bit fuzzy, right? So that's observational noise. That one I can possibly deal with, because if I unfold it properly, then it mitigates the effect of observational noise. But when we choose these embedding methods, the aim is not to reduce noise. The aim is to reduce the impact of noise on our embedding method, because we can't do anything to reduce noise unless we do things like Kalman filters or we average things. But the moment you do these, you are actually inherently changing the dynamics already, because you're changing your observations, right? So to reduce the impact of noise, we can have a few ways, right? We could truncate our observations at a certain point, which means our observations are accurate to however many decimal places. That means you bound the noise. That's kind of just going around the problem. That's not fixing the problem. We could average or coarsen our observations, and this averaging here is a little bit different to averaging there. And I'm going to call this partitioning for now. Or we could convert into what we call symbolic dynamics, which is in your phase space, we want to go from being continuous into discrete, right? We want to deal with, we want to make this problem a bit simpler, because if we do the full state space, it's a bit too complicated. I won't go into that, but Essentially, all I'm saying is when I say what a partition is, I'm taking face space and I'm chopping it into little bits, into little regions, such that any point in space only belongs to one region at a time. And so what we're going to do here is what we call attraction networks. We're going to say, how do we simplify our analysis? We don't want to deal with the full phase space. We've constructed it. We don't want to deal with all the details because it's very messy. How can we simplify it so that it makes our computation a little bit easier? Well, to simplify it means we need to just find a way to divide this large dimensional space, state space, into smaller regions. And the way we do that is what we say symbolic dynamics. And we're going to, the next picture should be some pictures here. So essentially what we're doing, we start with a time series. We do your delay embedding, which is just like versions, right? Now, these are actually all points. So we see the points in space, and we say, we're going to cut, we're going to divide state space such that we're going to merge them so that, let's say, we have two observations here. You take the average, put them there. And then we say, we get a simplified form, and we reduce the count of points. And then we're going to ask, how do we capture the evolution on that? We say, typically, these points go there. So we're going to link these two directions together. So what happens is, it's a bit complicated, but essentially, we're kind of reducing our attractor, the messy Lorentz attractor, for example, into a network, literally a network with nodes. Each node now corresponds to a region in phase space. And instead of talking about evolution in phase space in the trajectory, we say, if we observe, if I'm in region A, where's my next region? Region B, region C, that kind of thing, right? And because it's a network, you can kind of plot it in very nice pictures like this. And this solves the issue of high dimension, because now we're not talking about dimension anymore, right? We just split from continuous phase space into just this finite number of nodes. We just have to deal with nodes. And we also keep the dynamics because we can evolve along the nodes, can move from node to node. And we don't have to worry about noise because we now have partitions, right? Where I belong to a region. As long as the noise size is smaller than the width of my region, that's fine. I'll skip that. So what happens next is, this is what happens when you do it to Lorentz, right? So this is a representation of the 3D Lorentz attractor, but as a network. So actually, each of these corners here is actually a node, right? I've chopped up phase space R3 into little blocks, which are the nodes. And because you can learn the typical, like if I'm in this node, where do I typically go next historically? You can do a random walk on this graph to produce fake data, right? So this is my original stuff. This was used to create that. If I do a random walk on this graph now, and I keep track of the positions, I can recover fake data. There's no machine learning here in the sense of there is no convolutional neural network. It's literally fully from data. And I can do even more interesting stuff. So this is ECG data of a healthy person's ECG, only one channel. You do the same embedding thing, right? You convert it to a network. So this is dealing with dimension and noise now. And you do a random walk on that. And you get something which, okay, if you present it to a doctor, you see that ECG, you'd be very worried, right? This person is not alive anymore. But the thing is, it captures a lot of the similar behaviors you expect, right? So that's one application of this reduction, going from time series to networks. But we can also use it for more practical purposes, right? If I know that, let's say the time series is someone's heart ECG, and it typically follows this trajectory on the network, right? Typically follows this random walk. What happens if I suddenly observe that it's kind of going off what I normally expect? We can use that to flag whether someone might be having a heart attack, something of the sort. So, hold on. So, what we've done here. Where was it? I'm trying to find it. Yeah, here we go. So essentially, I have ECG. I have the healthy version, And somewhere along the ECG, the person has ventricular fibrillation, which is essentially a heart attack, right? And if you compare the two, you compare the delay embedding, the healthy is the blue, and somewhere along the line, it becomes red, right? What I do is I convert this into that network kind of thing. I've kind of put it in space here, but essentially now they're nodes. And I'm going to ask, okay, I'm traveling along, moving along the nodes, and I ask, is my movement normal within the realm of normal? Is it surprising or is it not surprising? And I kind of move along, and then somewhere along the line, which is like here, it bumps off a little bit. It's red because I'm going to say, okay, that's a bit weird, but maybe it's just an off chance, it's just a random thing. So because I suddenly go back on, but then it bumps off again. And all these, you constantly ask, is this normal? Is this normal? If you build up enough abnormal observations, then you can flag that the person's having a heart attack. So you can think of an application for this is if you have your smartwatch that's measuring your ECG the whole time, because ECG is pretty easy. You can use this to automate the detection of someone's heart attack, and then you can send it to hospital or whatever. And essentially, this is what this looks like. The blue is how much data we train on for the normal state to construct that factor. And then what happens is X is where the person was observed to have a heart attack. And red is where you're flagging that, the algorithm is flagging that it's heart attack. Essentially, for almost all cases, we can get, and this is very small, 5 to 10 seconds before they have a heart attack. But sometimes there are cases where it's like a whole 5 minutes. Very rare, but essentially there's that. Again, this is an example of in between now. So previously we had full embedding just on the time series. Now we have embedding using network things to try and simplify the problem. And this leads to the last part, which is ordinal networks. And now we're going to almost fully network type stuff now, with a bit of time series. So networks for time series. And a lot of the work here and a lot of the pictures here, I'm going to credit it's not me. It's my colleague Zara Shariari at UWA. So she's the ordinal networks person. So if there's any mistakes in the graphs here, it's not me. But essentially, if I'm given a time series like this, how do I convert this to a network? Previously, we said you can construct an embedding and then simplify it into a network. An alternative way is to do what we call ordinal symbols. So let's say we have 3 points in a time series, 1, 2, 3. We can represent this as a symbol or label, for example, 2, 1, 3. So amplitude ranking says that the way we write this is this symbol is given by the second thing is the highest amplitude, followed by the first point, followed by the third point. And so I can represent this group of 3 points as a single coordinate or single thing. That's one way of doing it. The other way of defining an ordinal symbol is if I have 3 points, I can rank by chronological. So it says here is that I think the third, hold on. So the lowest point was the third point, the second lowest point was the first point, and then the highest point is the second point. I'm gonna preface by saying it doesn't matter which one you pick, just pick one. They perform the exact same, right? Normally this one is more intuitive for me. That one is confusing. But when you read the papers, right, they just pick one and they are not consistent. Just as long as there is a way to map the ordering of the heights to a symbol, that's the main idea. And so, well, you have 3 points, you can have all these multiple cases, right? You can have all increasing like this, and that means you can replace any 3 points with a symbol. There. So now back to the time series. I take 3 points, space across by 1, right? So this 3 points will map to a symbol 2, 1, 3. I take the next 3 points, then that's another symbol 2, 3, 1. I can keep going, and the way I'm shifting my window, there are a few things you need to consider. The first thing is what is the width of the window, right? And this is where it's similar to the delay embedding. We also need to define the lag. So here the lag is 2, right? We skip 1 point at a given time. And then, so the length of the window, the width is how much the window moves across by, and the order dimensions. So at every point, I'm only including 3 data sets to convert into one symbol, right? Now, this should give a little bit of alarm bell because here I put m equals 3, and I can have, for m equals 3, I have 1, 2, 3, 4, 5, 6, right? If I have m equals 4, I'm going to have 12 possible symbols. I don't want to do m equals 10. Factorially large, right? The nice part is for most cases, you don't actually use all the 10 factorial. You only use a small subset of them. The rest are what we call, they've been called forbidden sequences because they just don't appear in the time series. So, but in the worst case, it's factorial. And so this idea of converting time series into symbols forms the basis of ordinal time series analysis and symbolic dynamics. And you ask, well, there's lags here and lags embedding. What's the relationship between the two? So ordinal methods basically try to simplify previously what was the phase space dynamics, which is continuous or something, try to simplify it into discrete and symbolic dynamics. Essentially, make the data simpler so that we deal with noise a bit better, we deal with fuzziness, all that kind of thing a little bit better. But it's also very closely related to delay embedding. In fact, I don't know if anybody's proved this yet, but my pet theory is it's essentially a delay embedding built in, right? And if we track, when we ask, okay, typically this symbol tends to go to like 213 tends to lead to 312 in the next time step. We track how often that happens, and we can construct a network from that, which says this node is symbol 213, right? And oftentimes, 90% of the time, it goes to symbol 312. So I'm going to do a link between these two nodes. And this is exactly what we did. So here's a slide which I've stolen from Elizabeth Munch from a really, really good talk. If you go to the UWA Complex Systems seminar, there's a Google site somewhere with all the talks historically we've done. This was 2022. Basically, it's actually a nice animation. I just had to screenshot. What we have here is just pick 3 points. This 3 points corresponds to symbol number 4. Whatever, I guess this case would be 1, 1, 3, 2, something like that, right? That's symbol number 4. But the main point, and you're sliding this across, and the main point here is that periodicities in your signal are preserved and becomes periodic in your ordinal sequence, right? And so that's that part. So I convince you that reducing your accuracy from continuous to symbolic, discrete, a lot of things get preserved. Maybe not your fractal part, but actually I think the fractal part, someone's done it recently, but that part's there. But then you ask, how is it related to delay embedding? Because essentially what you're inducing here, remember when we said we were partitioning phase space using the nodes before? This also does a partition. But the partitioning here is a very specific partitioning. It partitions by hyperplanes. So symbol 1 here, or symbol 4 here, corresponds to, within delay embedded space, corresponds to the case where the trajectory is in this partition, right? If I'm in symbol 3, for example, I'm in that partition. So imagine this this red dot is kind of moving. It says, well, typically, if I'm in symbol 6, I tend to move to symbol 4, and I tend to move to symbol 2, then 1, then 3, then 5, and then it goes in that way, right? And that the way that transitions you can use to make a network, right? Because you imagine you have 6 nodes. Node 6 will lead to node 4, will lead to node 2, will lead to node 1 all the time, and that's how it goes. And that's how it goes from a network. So this is another time series. But imagine if your symbols progress like this. So 213 progresses to 231, progresses to that, or blue, then red, then green, then blue and red. The transitions between these symbols, you can write it as an adjacency matrix, which you can then write as a network. And this network is very similar to the network we had before, but previously, nodes represented points in phase space. Here, nodes represent also regions, but regions defined by these hyperplanes. And this then forms the basis of what we call an ordinal transition network. And the idea here is a large proportion of the dynamics in the original time series it's still in here. It just looks a bit different. But computation, this is way simpler, right? Instead of dealing with your time series of your data, you now deal with just nodes, like segments. And whether it's nice is in this area called Poincare maps. So in this one is less so useful in application, but it's more of a fun little thing to think about in dynamical systems. So Poincare maps are a very nice way for us to analyze complicated systems. So if I have a system, continuous flow in, let's say, 3 dimensions, and I don't want to study 3 dimensions, I want to simplify my problem, I can go 1 dimension lower and study the map instead. And how we define this map, imagine the flow is like this. We take a little cardboard, like a panel, and we say, instead of studying the whole trajectory, I just study where it intersects with that little board. And I'm studying the point of intersection, which means instead of studying the 3D evolution along this line, which is in 3 dimensions, I study the 2D discrete jump evolution of where it intersects. So it's a map now from x1 to x2 to x3, so forth. So the idea behind Poincare sections is, from a mathematics standpoint, is that it simplifies the problem by 1 dimension. That's the main thing. But figuring out where to put your little placard is very hard, and it's not straightforward. There's a lot of ways to do it, but the question is, how do we automate that? How do we make a nice way of doing that? Turns out, if you do the first return map, that's a very standard way for Lorentz. You get this thing, okay? But if you go the other way route, you do ordinal symbols, and you calculate a few things, and you order by what we call the entropy of the network. So the network you create, after that, you calculate the entropy. You get a whole family of Poincare maps, right? And they look very similar because they are measuring the same thing. But a nice feature about this is because ordinal networks intentionally reduce the resolution of things to deal with noise a bit better. This first return maps actually are more robust to noise. So if you just did your traditional first return map, the performance quickly degrades when you have a very bad signal to noise ratio. But with ordinal return maps, because you're intentionally looking at just the ordering, you're reducing the impact of observational noise. Those return maps tend to be quite nice, even for low signal to noise ratios. Yes, and I think, yeah, so that was essentially 3 main areas. So we started off full time series and embedding. We got this in between where we want to deal with the dimensionality a little bit. So we have networks to try and deal with it. And then we went into a method which jumps straight into networks with various applications, one on the more theoretical, some on the between with applications like detection, some on the more prediction kind of thing. Yes. That's all it is.
So I guess it's a bit different from what we usually do.
Yep.
In terms of networks, but now we're looking at the networks in terms of quantifying the dynamics.
Yes.
Yeah. So Hunaini,
Hunaini, do you have a question?
She is going to do ordinal networks on time series.
Yes.
She's the lecturer for Universal.
Oh, yes.
Yeah. So she said she has a few questions about because she's looking at Zara's paper on OPN. And
yeah.
One is ordinal networks and one is ordinal partition network. Or is it the same thing?
So ordinal, it should be the same. So
then we go back to the figure.
Yeah.
That has all the and this one.
Yeah. So ordinal partition networks is using the transitions to construct the network, right? So the network we get in is what we call the ordinal partition network. It is also called the ordinal transition network because you're looking at transitions between symbols. Yeah, but they're all the same. Or they're also called ordinal networks. Yeah. As far as I know.
So, and in the embedding part, I think usually the question I get is because, and usually we use small time lags, time lags are very small, 2 or 3.
That's our normal.
Yeah, in our previous paper, and then I saw that sampai 100 something.
Oh, well, the time lags are entirely dependent on what your resolution of your sampling time. Because the usefulness of a time lag is entirely affected by the dynamics. That's what causes embedding to work. But it's a bit more complicated. So Parkin's delayed embedding primarily works. It works well for flows. For maps, I think it's originally defined on maps. So it should work for maps, but then you would only do one level. Because for Tarkin's delay embedding, it's originally defined as it's defined as discrete maps of evolution operator. So it should work in my mind, I think, but I don't know how well. I've never done it with maps before. But in that case, you probably will be doing only very small. Yeah.
Can I ask you a question about the state partition with symbolic numbers?
Yes.
How do you decide on the number of partition?
Right.
The states.
Usually so that's a very good question. So normally embedding, you would do all the fractal dimension kind of thing. Ordinal networks, we usually, we first try to go where it's computationally feasible, which usually limits at 7, right? And then from there, we usually have, we look at the application we're looking at. If we're, let's say, trying to do prediction, then we calculate a few scores for the prediction, and we try to trim it down to the point where the scores don't get penalized too much. So it's an adjustment process. Because the algorithm doesn't scale dimension the same way as how your normal state space methods do, right? Because here it's a vectorial scaling. Yeah.
What kind of question that? When you release the dimension from, say, continuous case to discrete case, releasing dimension. What kind of question that you can still ask in the discrete case, which you can't answer in this continuous case?
So if we look at the case for the heart attack data, right? I think you can still ask the same question in a continuous case, but it will be computationally very hard to do. So a lot of these transformations to go into the discrete, you can do everything in a continuous case, right? But is that computationally feasible, right?
That's the constraint.
Yeah, exactly. Because you're now trying to quantify, in that case, we're trying to quantify this bit here, which is how surprising an observation is, right? Trying to quantify how surprising an observation is of a trajectory means you need to start taking metrics and distances from an average trajectory and then trying to normalize those distances. Whereas if you start doing in terms of a network, instead of talking about distances, you just talk about the entropy of the transitions, which is a way simpler measure. And calculation-wise, it's also much simpler.
I don't have any other please. Anything else is okay.
We are doing question about and the right line involve embedding also.
Yes.
Right. So is there any particular embedding method that you recommend for
Honestly,
you like to compare with our situation?
Okay, which means is your time series like a map type or is it continuous but a discrete sample? What kind of time series is it?
It's
The financial time.
Okay.
It's just
Yeah.
Usually it's the uniform time embedding, the uniform version.
I think so. From what I know about financial time series, I feel like the first test before you even do any dynamics or Bertrand homology is to do a surrogate test to see whether what you observe is significantly different from a random process. You need to test whether your observed time series has dynamics that are not just a result of a random process.
Or you want to test for stochastic?
Similar. So you can have a process that is stochastic, but with a dynamic driving component. Right? So essentially what we're looking here is how is it different? Is it very different to a normal just autoregressive process? Is it significantly different to a normal noise process? Because you can have stochasticity in, so for example, if you have a dynamical system, okay, like this, right? So if I have x that is equal to fx plus qt, but qt is a not random process, this would still be a stochastic system, but the overall average dynamics would still follow some kind of deterministic behavior. So you would still say that's stochastic, but then a lot of embedding methods would still work. But so the test you need to do is does your system have a deterministic component, or is it entirely mostly just a random process, right? And this is where we get into like surrogate testing, because you define surrogate processes and then use calculate certain invariant measures to do the hypothesis testing, to do this test first. And I suspect a lot of financial time series is very much either there is deterministic, but this stochastic term is very large, or is best represented as a stochastic process. So when you start embedding these things, a lot of stochastic processes in the point cloud just look like a mess, right? And when you do persistent homology, then the most useful homology dimension would be H0, which is essentially just talks about the density of points. And if that's your only useful part, then because there's no loops, right? Loops imply the existence of dynamics. If it's mostly H0, you're probably better off doing a stochastic kind of predictor. Yeah. Does that answer the question?
Yeah.
Actually, I asked Michael this question, and his answer was not similar to yours. But if you want to compare two time series, some sort of coupling and compare the dimensions,
that's different.
Yeah.
Because you can have two noises that are correlated in some complicated way. Yeah.
So I think with Naini, that's the direction that we're going. So she's also looking at financial data because that's the data we have. So it's the comparing part, the comparing the dynamics, and not just depending on one time series that like you get something instead on.
It's kind of like saying you have this and this is noise, but you have another set of noise which is similar. So you're hoping that you can cancel out this, and what's left is the coupling component, which you're hoping is deterministic, which may not be.
But we can try.
I think probably because he's taught me persona, probably why our answers are very similar. But I think I believe his stance is that a lot of this is a lot of financial data is highly correlated with trading volume.
Yes.
So trading volume often precedes large movements in price because humans are very reactionary. So your best predictor is literally just trading volume. And I wouldn't be surprised if it's less dynamic and more like a lag proportional kind of thing.
Probably.
If you took,
Maybe not some sort of linear dynamic.
No, it'll probably be like a constant or similar to a constant, like a linear predictor.
All right, you're talking about noise, right? So you're talking about dimension. You say that usually. So I was wondering if we increase the dimension of the embedding, Does that somehow, I don't know, maybe reduce noise or
So you can never really reduce noise, but you
Oh,
can
you
make your method more robust to noise.
Oh, yeah.
Right? So when you increase the dimension, if your noise is kind of pushing your data all over the place to begin with, increasing your dimension is just going to make your point cloud also still all over the place, but in a higher dimension. And you can keep increasing the dimension further. What's going to happen is that a lot of your numerical methods are going to struggle really badly, right? Because a lot of numerical methods don't scale well with dimension. Persistent homology, no, persistent homology is okay to mention because you just need a distance matrix at the end. Yeah, but so one way to illustrate this is, where was that plot? Okay, not this one, right? Increasing the dimension will go from maybe this is a figure 8 to this kind of shape with a curvature, right? But the thing to note is that the important features will always be preserved. The structure is always preserved when you increase dimension, right? Where in the same way, the noisy hairball will always be preserved in increasing dimension, right? So you can't make structure appear by increasing dimension. Yeah.
But, we were wondering about the tagged embedding. The tagged embedding works because you exceed the original dimension, right? So that's one of the reasons why
So Tucken's embedding not exceed the minimal dimension, but it says that if you have sufficiently large dimension, then the homeomorphism exists.
That's the reason why
Because if your dimension is too small, then you have chopped up information, right? But that assumes that there is dynamical information in there to begin with, right? If you just have cloud of points and you increase the dimension, the cloud of points is still going to stay a cloud of points. It's going to stay like a blob, right? Increasing the dimension is not going to make the points suddenly align with each other and form a shape, right? But if it originally was like a donut shape, small dimension, yes, it'll look like very messy, but that's the case where because there's actually information in there, when you increase the dimension, the donut shape will be more clear. So it's kind of like going from here to here. The donut shape is also there, right? But that's a case where there's actually information there, and that's why increasing it works. Sorry, I didn't do any infectious diseases stuff. I can talk about that and social network stuff later. I didn't prepare. I have stuff, but I didn't prepare it. Slides for it. It'll be off the cuff.
If there's no question, we can have more discussions if you want. Do it. Thank you, Eugene.
Thank you for having me.
Excellent.